Good morning, everyone, and welcome to track 2 of the 2021 Midwest Manure Summit. My name is Alyssa Seefelt, and I'm the agriculture educator with Extension in Eau Claire County, and I'm going to be your host for this track. As with the first session, do please keep your microphone muted and videos off during the webinar. The mute and the video controls are located at the bottom left hand of your screen. Also, please do feel free to type chat questions for our presenters. That chat box is at the bottom of your screen, and you can type that in at any time. We'll try to get to as many questions as we can as time allows. With that, I would like to introduce our first speaker, Dr. Robert Levine. Robert holds a PhD in chemical engineering from the University of Michigan and a BA in molecular biology and biochemistry from Middlebury College. He's the serial entrepreneur with over 10 years of experience in the animal feed, renewable energy, and waste energy spaces. Before leading the team at Digested Organics, he co-founded and later sold an animal feed biotech business producing immune-promoting ingredients from LE. Dr. Levine will be presenting Ammonia Capture for the organic market, and this session has been graciously sponsored by Oxbow. And with that, Dr. Levine, the floor is yours.
Great, thank you very much, and good morning to everybody. It's a pleasure to be here and have this opportunity, and thanks to all the organizers and the sponsor for making this possible. So I really appreciate it. Digested Organics is a specialty filtration company. We're based here in Michigan, outside of the Detroit area, and we've done work throughout the country and throughout the world, helping waste producers create new value from their waste streams. And in particular today, we'll be talking about what we can do with manure. A little bit of background about myself. As our moderator just mentioned, my background is in chemical engineering, before that in molecular biology and biochemistry. And I studied in Vermont, where I first got introduced to dairy farmers. I worked with digestate from traditional digesters and how we could grow algae to make biodiesel. This was about 15 years ago during a lot of the biodiesel and kind of renewable fuels from algae as that was really becoming more popular. Ended up then working for many years, founded a company that did animal feed ingredients with algae, and now I'm running Digested Organics. We started the company in 2013. And I'll just mention Don Heilman. He's probably in the session here today as well, but he is out of Middleton, Wisconsin. He does a lot of work with farmers throughout the Midwest, and is a really good resource if you're interested in learning more. And he's also just worked probably 20 plus years with a lot of these farmer-led watershed action groups, and so he's very knowledgeable about the space in Wisconsin in particular. So I want to frame my discussion before launching into the technology and some of the numbers around manure, ammonia levels and processing, kind of just frame it in what we see happening today. So in very broad, simplistic terms, manure management has been done in a very similar way for a very long time. And that is depicted here. So animals produce waste. Sometimes we remove solids from that waste. I mean, you're using a screw press or a slope screen. We put that waste into an open air lagoon, an anaerobic lagoon typically, that releases methane and ammonia to the atmosphere, causing significant pollution. And then we land apply that manure when we can. And the problem is really that last part. If we had limitless amounts of land with absolutely no nutrient limitations, and we had just arrived here, we wouldn't have the challenges we have today. But the reality is we've been farming the same land for a very long time. As the opening speaker, Dr. Zavalis, spoke about, we have significant nutrient imbalances in terms of where the phosphorus is and where other nutrients are. We have heightening regulations to try to help manage that nutrient runoff and some of the issues around that. And then we have changing weather patterns. We have a climate change situation that'll bring drought to certain areas and more severe rainfall to other areas, and it makes it much more difficult for farmers to keep doing what they've been doing through land application. So it makes it more costly, less reliable, and introduces challenges to the environment as a result. So what we've tried to develop is a closed loop platform where we can take this high strength wastewater, in this case manure, we can put it through a filtration system to separate the water and make value-added fertilizer products. And in most cases, that water can go back to the animal for the animal to drink. You know, cows in particular, obviously, drinking a lot of water to produce a liquid product as milk. And then we can grow crops to feed those animals or to feed humans or maybe other animals. So sometimes that loop is truly a circle in a very tight way around a specific farm, let's say. But in other cases, we're sort of spinning off the fertilizer component out of that loop to a nearby regional, let's say, watershed or nearby areas that can use those nutrients. And so by doing this, we're hoping to, one, derive significant value for the waste generator, in this case, the farmer or the project developer who's perhaps running a digester project. We're hoping to improve the environmental performance of these facilities, as well as create circular economies. So a little bit about how we do that. We have 4 core technologies. Today, I'm really going to be talking about 2 of them and showing you some examples of how this plays out on a typical large, sort of Wisconsin dairy farm. But the 4 technologies we have to capture nutrients and reclaim water is a spiral brush filter. This is a self-cleaning screen. We have a stainless steel ultrafilter, which is a tubular membrane filtration system. We have a process we call 2-step reverse osmosis, which actually removes the water from the wastewater. And then we have membrane bioreactors, which are essentially high-rate digesters that use ultrafiltration. And all of our processes, something that you'll hear me talk a lot about, is that these are all polymer-free and don't use any chemical additives. So that means that all the products that we generate are going to be organic certified. So just briefly here, this is the spiral brush filter. It's ideal when we're talking about manure for things like dairy flush water or lagoon effluent before you're trying to irrigate, let's say, to reduce solids, either loading to your lagoon or to clogging nozzles in your irrigator. And this sometimes can be used as a sort of a pre-treatment to some of the ammonia capture technology that I'll tell you about momentarily. And essentially, it is a wedge wire screen, so it's not that different from what a screw press screen looks like, but it has a self-cleaning brush in it instead of an auger. And that brush is spinning at a decent RPM to create a cleaning effect and to pull the solids down to the bottom. So it actually, manure would come into the top flange. Hopefully you can see my little red dot. Goes through the inside of the screen and out the bottom as a filtrate, as a cleaned product. And then the solids accumulate inside and get purged out the bottom in an automated fashion. And it doesn't have to shut down to backflush the way maybe a filter press would or a sand filter would. It's continuously processing material and then just purges material at the bottom when it needs to. So this is a very relatively low-cost platform. It can do high volumes. So especially if farmers are looking to clean up flush water or keep solids out of their lagoons, things like that. This is an ideal tool for that. And sometimes that pre-treatment gets us to the next step where we'll do the ammonia processing. The second technology is our stainless steel ultrafiltration. This is a porous stainless steel tube. So that picture in the top right is what the actual membrane looks like. And if you're looking at it, you might say that just looks like a pipe, and it certainly does. It's 3/4 inch internal diameter, but it's actually a porous pipe. So we make it from, we start from, it's essentially sintered stainless steel, so it kind of looks like a sand, it looks like powder, and we form it into the shape of a pipe under pressure, and then it gets essentially baked to harden it. And that membrane is very, very robust and also has very, very small pores. So the average pore size is 0.02 microns, and that is about 10 times smaller than the typical bacteria. So it essentially produces a very clean filtrate that has no bacteria in it, very little phosphorus, very little organic nitrogen, and it does it while being in this stainless steel system. So it's very abrasion resistant. There's actually no moving parts inside the filter unit. There's just a centrifugal pump that circulates the material through it. So it's designed to be robust enough for manure. And that traditionally has been why manure has not been filtered using ultrafiltration, let's say, is because it's just a very difficult material to handle. There's fibers in it, there's sand and grit in it, there's minerals from the cows being fed. So it is traditionally just a difficult material to handle. And we feel like this is a platform that we've now run the system at a farm for over 3 years. And we think this is a platform that can really stand up to manure and provide the separation we need to then go after different nutrient components. So a little bit more detail on the ultrafiltration. This is actually what it looks like if you opened up one of the modules and you saw all the individual tubes. So this is what the tube sheet looks like. That's what it's called at the edge of the sort of the end of the module. Some of the benefits of this platform relative to other nutrient separation technologies are that we're not using any polymers, so we don't have the cost for that. We don't have to handle those chemicals. And again, our fertilizer products can be organic certified. We have a very high reliability. So these stainless steel tubes are welded in place and essentially will produce the same quality filtrate day in and day out with really very little that can upset that. So it's not like you can sort of have a bad day and let more dirt through the tubes, or be like a biological system where sometimes the bacteria in the digester, let's say, are doing really well, and sometimes they get out of whack because maybe it becomes too acidic or too basic. So it's a mechanical filter process that's very robust. The next point is, it's a very clean process because it's all in pipe. So there's no open vat of manure. We're not bubbling air through the manure like a DAP. We're doing nothing to create odors. It's all in pipe. And that also helps reduce the amount of ammonia that would otherwise be lost, which, as we'll also talk about, is a product that we want to make. Again, it creates a valuable separation. So, we believe in most cases that the parts of something are more valuable when they are apart than when they are together. So in this case, when I can turn manure into water and organic fertilizer, that's obviously much more valuable in those two pieces than it was together when it was just manure. And this accomplishes that for us. And something we'll talk about on the next slide is how we can also capture volatile solids to enhance digestion. And I'll show how that relates to sort of sustainability in general, but also, again, to ammonia capture. And then it's fully automated. So it's a very simplistic system, relatively speaking, but we put a lot of thought into the automation around it. So it's not another item that the farmer or the project developer really has to worry a lot about maintaining because it's so simple to use and so automated. So this is what it looks like. This is digested dairy manure in the mug on the left, and this is the ultrafilter permeate filtrate on the right. And so what we've done is we've taken the digestate. Usually this is after a screw press to remove large fibers. We've ultrafiltered it, and we're showing you the permeate, and then the concentrate would look very similar to the feed, but just be thicker. And so what's unique about it is that about 95% of the phosphorus and the organic nitrogen are retained in the concentrate, which is also known as the retentate. So basically it means that they don't get into the permeate. So this material that some people call tea water is very, very low in phosphorus and organic nitrogen. It essentially has no pathogens or suspended solids. So again, we've removed all the bacteria. And it is also very, very low in volatile solids. And volatile solids, for those that might not be familiar, are the solids and the organic matter that gets converted into biogas in a digester. So you want to put as much volatile solids in your digester as you can to make as much gas as you can. And if you digest manure and then the volatile solids that didn't get digested come out the back end and go into your lagoon, those can continue to degrade anaerobically, release their methane to the environment, and you didn't capture the gas value that you could have. Plus, there's the environmental degradation from that release. So another benefit beyond fertilizer production here is that if we ultrafilter manure, we can actually capture those undigested volatile solids and do a few things with them. So we can put them back in the digester to digest them again. That's essentially what we do when we build our membrane bioreactors. Is we take digestate, we ultrafilter, and we put the ultrafilter concentrate back in the digester. We can take that concentrate to an aerobic situation like composting, which I'm about to talk about, Or we can take it to some kind of secondary storage. Maybe it's a covered anaerobic lagoon where we can continue to capture that gas. So we always encourage people to think holistically about their manure management situation. And the UF, which is the abbreviation for ultrafilter, the UF is a tool that kind of accomplishes many jobs as we are getting closer and closer towards making clean water and ammonia. This is an example of what the concentrate looks like here on the right. We were part of the Vermont Phosphorus Innovation Challenge, where they sponsored us to produce a pilot unit, which was actually going to deploy in the next couple months to dairy farms in Vermont to essentially capture phosphorus from manure. So the idea is that because the UF removes 95% of the phosphorus, we can very cost effectively concentrate the phosphorus into a small volume, usually about 20 to 25% of the original volume. And then we can stabilize that further by doing something like composting, for example. And so here we worked with a very large composter in the state of Vermont, outside of Middlebury, and we're able to show that we could create a recipe where we mixed ultrafilter concentrate with dairy fiber from screw presses, along with other normal, dry ingredients that composter was using at the time to make recipes where the compost turned out in certain ways better than a control pile of compost. So it heated up faster, it reached maturity faster, it had higher levels of nutrients, and it was in terms of kind of going back a little bit to what Dr. Zavala said about, what's the cost per pound of phosphorus control and things like that. This is actually a dramatically lower cost solution than a lot of other solutions that farmers are doing today. So not the topic we're talking about today, but something that, again, it's an ancillary benefit that along the way towards making clean water and ammonia, we're getting a concentrate of our phosphorus, and that can provide a lot of watershed benefits. So after we've ultrafiltered, we have our UF permeate. So that's the mug on the left. And now we need to, I'll pause for a second and say, for some projects and for some farms, that accomplishes most of their nutrient management goals, right? So maybe phosphorus is their main goal, and they want to irrigate with a phosphorus-free tea water that doesn't have any pathogens in it. Lots of situations where the UF solves most of the problem, provides a lot of benefit. Here we want to go one step further and say, now I want true volume reduction, and I want clean water, and I want fertilizer. So this is where our second stage process comes in. We call it two-step reverse osmosis. It is a combination of two filtration technologies. The first is actually called forward osmosis, and that is what you see here in these membrane stacks. We call them stacks. So each sort of square element in a stack is a forward osmosis membrane. And the best way to explain how this works is sort of to imagine my hand like a piece of membrane paper, and on one side is wastewater, which is in this case is our UF permeate, and on the other side is salt water. And the salt water is actually saltier than the wastewater, and so it draws the water through the membrane in the forward osmotic direction. That's why it's called forward osmosis. It's kind of like it's working backwards from reverse osmosis. So we're basically drawing the water out of the wastewater and into salt water. And then we put that salt water into a reverse osmosis system to make clean water and recycle the salt, because we don't want to be purchasing salt all the time, obviously. We sort of charge the system with salt on day one. We're trying to keep that salt in a loop, throughout time, and let the forward osmosis system do the work of dewatering the material. And the reason this is so unique is because traditional reverse osmosis really struggles with wastewaters like manure, even ultrafiltered manure, because there's still so much organic matter in it. There's humates and other dissolved organics that, when put into an RO at very high pressure, can cause premature membrane fouling, failure, a lot of downtime for cleaning, very, very problematic. So we think that this platform is unique in the sense that it runs at very low pressures and uses that natural force of the salt gradient to draw the water out. And as a result, it can run very long times between cleaning and performs at relatively low energy costs because we don't need to run pumps at such high pressures. So again, this is the platform we've developed for essentially pulling water out of the manure or the ultrafiltered manure, and compared to an evaporator, which would be another technology and something we're going to talk about in a minute, it's quite a bit more cost effective. So it's very energy intensive to evaporate water, unless you're at some unique situation where you have a lot of waste heat available. Buying natural gas to run an evaporator to evaporate the water from manure is quite expensive. So our philosophy is always to use membranes to try to remove as much water as possible before going to some kind of evaporation step. So on the left here, you have your UF permeate. In the middle, you have what we call our forward osmosis concentrate, or FO concentrate. And on the right, you have a mug of clean water. And that water has been permitted to put into a river. So, this was a picture actually taken at our facility in Majestic Crossing in Wisconsin. So it's permitted for discharge to the Sheboygan River. It is clean enough for cows to drink. And it's certainly a resource that we would encourage the farmer or the project developer to reuse, responsibly, again, as part of a holistic approach to manure management. And certainly, I know a lot of you are based in Wisconsin, and certainly there are some places in Wisconsin where groundwater is more scarce, or the cost of a well is high, or a high capacity well is high. But for the most part, what we hear from farmers in Wisconsin is that the water has value in the fact that now you don't have to store it and haul it. So if I can turn 50% of your manure into water, which is now not in your lagoon and not being hauled out of your lagoon and put on your land, the value is the avoided cost of that storage and hauling and the complexities that go along with it, as I mentioned at the outset. In other places of the country, that water itself has value as water. So we do work in Colorado or Arizona or other places that are very dry, and farmers are actually buying water rights at very high rates, sometimes many cents per gallon, to feed their cows, so their cows are productive animals. And so it certainly makes sense to reuse that water to the extent possible when there's that sort of environmental pressure in a watershed that doesn't have a lot of water. But that's always something that I think will be taken on a case-by-case basis. So I think some milk buyers or milk processors are very comfortable with this idea. They know that this is advanced technology and kind of the future of where resource recovery is going. And I think other people do sort of have a yuck factor about it, to be, to put it bluntly. And I think it's certainly something that, it's being done with human sewage more and more, that human sewage gets treated to drinking quality levels and is then distributed. But it is sort of something that the industry is going to have to come to terms with and to learn about. And we don't expect it to happen overnight, but it is always, I think, interesting just to think about water as a valuable resource also. But it's typically very geographically dependent. So we've taken our UF permeate, we've created two new products: a fertilizer product called FO concentrate and a clean water. The FO concentrate, in some cases, again, that is sufficiently concentrated that the farm or the project developer is interested in using it or selling it as a fertilizer product. And so you have options, for example, like storing your ultrafilter concentrate and your FO concentrate in separate lagoons and then making custom blends. So maybe if you make a custom fertilizer blend for corn versus beans versus alfalfa, you can combine them, and then you sort of have all of your nutrients back together in one pile and then water separately. And so it's the same pounds of NPK that you had before, but now they're in dramatically less volume. So you can afford to haul them to fields that are potentially further away or use them differently. So I think there's a lot of optionality that this system presents to the farmer when planning your nutrient needs. And again, the ammonia, I should say, passes through the ultrafilter. So we'll get into some of the numbers in a minute, but the ammonia is soluble. So that means it's dissolved in the water and it passes through the ultrafilter tube and it gets concentrated in the two-step RO. So this darker liquid fertilizer is highly enriched in ammonia nitrogen, as well as potassium nitrogen. So it's really it's a high nitrogen, high potassium liquid product, but it's certainly nowhere near the levels that a farmer might expect in a conventional, fertilizer like a 24% aqueous ammonia nitrogen product, for example. It's more like between 0.5% and 1% nitrogen and potassium. So it's still relatively dilute, which means there's still a high cost to transport that material, which is why we'll talk in a second about kind of our final stage process in terms of fertilizer production. Before doing that, just want to mention again that all of our equipment is fully automated. This is a picture of actually our controls container at a system we installed in Kentucky. Our farmers have online dashboards where they can review how their system is performing, what the throughput was, the number of gallons of clean water it made. And I think it's important just to point out that a lot of farmers and project developers we work with have estimates of how much manure they have and how much water they use. And sometimes those estimates are really quite detailed and accurate. Other times they're not. And plus there's variation seasonally and with weather and whatnot. And so I think we strive to give this data to the farmer, to the project developer, so that they can take actionable decisions, based on the data. And so by actually knowing, what your throughput was every day, and then tying that to a nutrient analysis to understand where your pounds of NPK are going on a very detailed basis, I think can bring a lot of value. So that's something that we talk a lot about, is how do we through the automation that our system needs just to operate well, which is flow meters and pressure sensors and temperature sensors, things like that. How do we then package that data for our customers and the farmers to make the most use of it? All right, so this is sort of an overview of the processes that I just talked about. When we put it all together, we like to call it our Nutrient Concentration Water Reclamation Platform, or NCWR, a little bit of a mouthful, but basically, starting here on the left, you have manure from a barn or a digester. We're going to take it through some kind of a solids removal step. Here I'm showing a screw press, but it could be a slope screen, it could be a roller press, lots of ways to get fibers out. And these fibers are usually used for bedding if you're on a dairy. Sometimes they're composted or used as a soil amendment. The next step is ultrafiltration, like we talked about. Here we're removing the suspended solids, the pathogens, and the phosphorus. We're creating a fertilizer product called UF concentrate, which I think there's a lot of sort of along the lines of what we heard earlier about phosphorus management and how there's sort of imbalances. We've talked to a lot of dairy farmers who have manure, who have land right next to crop farmers who don't want to touch manure because they think it's too dilute and it's not worth their time to haul. And the dairy guys are desperately trying to get rid of the manure because they need help spreading these nutrients out. And their neighbors say, we don't want to help you. That's not worth our time. But when you show them an analysis of what UF concentrate has in it, which is essentially 3 or 4 times the amount of nitrogen and phosphorus, now I think that there's an opportunity to interest other stakeholders in a watershed to say, can you help me move these nutrients? They're now much more cost effective to move. And so we certainly would love to have conversations with folks around how do we set up situations where farmers can share those nutrients, whether it's sort of a community bank of tanks where we can store ultrafilter concentrate and then let crop farmers take it and distribute it more widely and more responsibly based on nutrient management plans. How do we make the economics around that phosphorus trading in a way work for everybody? And I think by concentrating the nutrients, we've gone a long way towards making that more possible, just because every tanker load going down the road has substantially more pounds of NPK in it than it did before. So in the middle here, you have that UF permeate, what people call tea water. We go to our 2-step reverse osmosis process. Here we're taking out, the color, the dissolved solids, the dissolved organics. We're making the FO concentrate fertilizer product. And And then we're making clean water. In the case of cow drinking water, usually we add an ultraviolet disinfection step at the end, even though it's sort of just a nice redundancy. You know, no bacteria got through the UF, nothing got through the FO, nothing got through the RO. It's really a truly redundant step at the end. And again, that water can be reused on site or discharged under an NPDES permit. So now let's put some numbers to all of this and kind of give you guys a little bit of a case study. So the numbers I'm going to show you are a little bit simplified just so I could use round numbers and keep it a little bit tidier. But essentially, we're going to start with 1,000 gallons of digestate. We're going to screw press it. Usually, we lose about 10% by volume in a fiber pile, leaving us with 900 gallons going to the ultrafilter. The ultrafilter will do about a 75-25 split. So we'll have 675 gallons of permeate and then 225 of concentrate. That goes to the two-step RO, becomes about 175 gallons of FO concentrate, which is that fertilizer product, and about 500 gallons of water. So this is about a 50% water recovery on a whole digestate basis, or about 55% on a liquid basis if you start with the 900 gallons out of the screw press. So now I'm just going to multiply all of those and say, now let's assume we have 100,000 gallons per day of material coming in, which is about a 3,000 to 3,500 cow dairy, which we see commonly throughout Wisconsin and in the Midwest. So the numbers are the same. They just got bigger. And now let's look at what's in that material typically. So I'm showing you, we've done both at our commercial site in Wisconsin, as well as dozens of other pilot tests with equipment on site at farms, lots of different dairies. So I pulled sort of a typical Wisconsin dairy that had a digester, which is a DVO style with a screw press, and then also a typical Indiana dairy. So both of these are digestate. You'll see that they're very similar. So the liquid pressate, we typically go to a farm and we pick up the pressate out of the screw press. The liquid pressate has 3.4% total solids or dry matter. And here at this farm, it was 3.8. We ultrafiltered that and created a permeate that was about 1% total solids, or 1.1%. And then the thickened product was between 8 and 9% total solids. And that's just based on how much permeate we removed in these tests was a little different. The ammonia content in milligrams per liter was about 2,030 in the raw material at the Wisconsin dairy, and it was about 2,400 at the Indiana dairy, so pretty similar. The UF permeate, in theory, should have the exact same amount of ammonia as the liquid pressate and the concentrate, because again, it's not it's a soluble molecule, so there's no reason for it to stay inside our tube or go outside the tube. It's gonna be distributed evenly everywhere. The difference we often see in lab testing is really around how the lab handles samples that show up looking like manure, which are treated like manure, and then samples that show up looking like permeate, which is to them more of a wastewater that looks like it's maybe coming out of maybe a municipal wastewater or an industrial wastewater. And so they actually provide more accurate analyses on the permeate than they do on the pressate. And so sometimes it leads to numbers that look a little off. But also, again, as many of you are probably familiar, it's very difficult to accurately sample manure. We're usually picking up 250 to 500 gallons of material at a time, taking it back, sampling it, trying to mix tanks, things like that. So none of these numbers are perfect. These are just, real numbers from real pilot tests. But I guess in theory, these numbers should really all be the same number, essentially. The organic nitrogen is usually about 55 to 60% of the total nitrogen. So here I'm showing you ammonia nitrogen, organic nitrogen, and then total nitrogen. And the total nitrogen, or TKN actually, is the sum of ammonia nitrogen and organic nitrogen. So those always sum up. And what you'll notice is that the ultrafilter removed the organic nitrogen substantially. So it went from 1620 to 110, went from 1416 to 204. And again, that's that effect we see with that very high organic nitrogen removal. And the reason for that is because that organic nitrogen is in larger particulate forms. So it's proteins, it's part of solids that are getting removed. And so that is leaving us with a permeate that is much more ammonia based in its total nitrogen platform, or I should say proportion. So it's about closer to 90% ammonia. So this number is the based on the liquid pressate. So let's say 50 to 60% of the total nitrogen in the pressate is ammonia, but in the UF permeate, it's more like 90%. So what I did is I took these numbers and I created a mock mass balance for the same flow rates with numbers that I basically just rounded numbers. So I assumed that the digestate came out of the digester at 5% solids. I put it through a screw press and made like a 10% volume cut at 20% solids, and out of the UF feed at 3.3% solids. So this is pretty similar to the data I just showed you in terms of the ammonia content, the organic nitrogen content. Essentially, I'm just modeling this for the UF feed, the UF permeate, UF concentrate, and then FO concentrate. So this is the concentrated UF permeate. So basically the 2,000, let's say 2,100 milligrams per liter of total nitrogen in the UF permeate becomes 8,200 ppm in the FO concentrate. So that's what happened when we removed all of that water. Down below, the units are now pounds per day. So you can think in concentration in percent and milligrams per liter, pounds per day. And what you can see here is that in terms of ammonia, we have something like 1,600 pounds per day of ammonia in the, let's say, starting material, and we're capturing about 1,100 in our FO concentrate. Obviously, we're losing some in the solids out of the screw press and some in the UF concentrate, which doesn't then go into our fertilizer product. But we're capturing a very high proportion of the total ammonia and the total nitrogen in this process. So going back to the same flow diagram, I've basically just added on one extra step where I've taken that 17,500 gallons of FO concentrate. I've put it through an evaporator, which removes water. I get to add to my water pile. So instead of making 50,000 gallons of water, I'm now making 65,300 gallons of water. And I've made 2,200 gallons of fertilizer. And that fertilizer is a 605 fertilizer. So this is that same chart you just saw. Now I've put another column on it for evaporator concentrate, which is our fertilizer product. And you'll see here that the total nitrogen is 65,000, which is 6.5%. And obviously, we're calling it a 6% fertilizer. Here I'm showing you that we're making it a little bit richer than that, which is typically what you do to guarantee your fertilizer label. So this process is capturing most of the nitrogen, and it's making a product that is about 6 to 6.5% nitrogen, and it's a liquid product. So even though the dry matter content is up around 40%, it's still a liquid product. It looks like sort of a thick, dark honey, but it's easily dilutable. It has no large suspended solids that would clog irrigation nozzles. It's essentially a condensed form of manure after ultrafiltration. So let's sort of summarize what just happened. So a farm that has 100,000 gallons per day of digestate and roughly, let's say, 3,500 cows just produced 800,000 gallons per year of liquid 605 fertilizer. And they've exported 439,000 pounds of nitrogen from their farm. That's nitrogen that used to be heading to their lagoon. Now, here's the interesting part. Most dairy farmers will tell you, I suppose swine as well, if you have an uncovered lagoon, you probably lose 30 to 50% of your ammonia nitrogen every year to volatilization. So that means that the ammonia that's in that liquid is volatilizing, becoming gaseous, going into the air and leaving your lagoon, and you never see it again. And there's different estimates for this. I pulled up a paper that showed it was about 25 to 50 grams per head per day, which for this example would be between 70 and 150,000 pounds per year of ammonia. So on the one hand, if you're the farmer who needs nitrogen to grow crops, let's say, you've just lost a lot of your nitrogen to the atmosphere, and you're not getting it back. That's also bad for the atmosphere. So ammonia is a precursor for particulate air pollution. It creates aerosols where basically it molecularly combines with sulfate to make ammonium sulfate and then nitrate to make ammonium nitrate. And that substantially reduces air quality, so it's dangerous for humans, it's dangerous for animals. And then those ammonium species do redeposit regionally over the course of days. And put the nitrogen in places where the nitrogen shouldn't be, right? So that could be sensitive watersheds that leads to eutrophication, algae blooms, dead zones. It's a substantial environmental problem that, really livestock production is essentially the largest source of ongoing ammonia emissions. And as a result, there's lots of regulators that would love to regulate that and to enforce measures for farms to have to reduce ammonia emissions from uncovered anaerobic lagoons. And so we do see evidence of that coming in certain places, and it's something that is another benefit of thinking about the technology that I just presented, because if you take the ammonia out of the material before it ever gets to the lagoon, you've solved that problem. There's nothing there to volatilize because you've removed the ammonia. On the flip side, the question is who's going to now buy this product? So you've made this 605 fertilizer. You didn't use any polymers in the process, so it's organic certified. And the question now is, well, who wants that? And the answer is organic farmers. And the reason is because if you're an organic grower, it's typically challenging to find good sources of organic nitrogen. There's guano, there's Chilean nitrate, there's fish emulsions, but those are often imported from far away, and they can be challenging depending on where you are to get those, and they can be challenging to use as well. So like fish is a very odorous product. Chilean nitrate comes with restrictions about when and how much you can use. They're often quite a bit more expensive, obviously, than conventional nitrogen. So it's a substantial challenge today in the US, at least, to find good sources of organic nitrogen fertilizers. And so if you're a conventional dairy farm or conventional swine operation producing manure, we can produce organic certified fertilizers from that manure on a conventional farm. So the value to the conventional farm is not that much, right? Like, if we just say nitrogen's worth half a dollar a pound, 50 cents a pound, the amount of nitrogen that I just exported, the 440,000 pounds per year, is something like $220,000 worth of conventional nitrogen. Whereas to an organic grower, that's far over $1 million worth of organic nitrogen. And so it's a very valuable product that can introduce a new revenue stream to an otherwise conventional farm. And so I think it's a really important point to understand that we can take manure from a conventional farm, process it responsibly with filtration, not introducing other chemicals, and produce a concentrated liquid fertilizer that provides a lot of value, and frankly can also help unlock an industry that's trying to grow. So organic crops are growing, as consumers' demand for organic produce continues, but we still, maybe, and it varies obviously regionally, but certainly with like traditional organic row crops, for example, like corn and wheat and rye and things like that, where you need a lot of nitrogen, the struggle has been around finding these readily available, cost-effective sources of nitrogen. And so I think, dairy farms and swine operations can be that missing link where they're often co-located with, for example, row crops of corn and wheat and things like that. And so we can essentially create organic nitrogen fertilizer plants on conventional farms to make a very unique organic fertilizer for the surrounding region. All right, so I'll sort of summarize and wrap up by kind of thinking about it with sort of two hats on. So one is the farmer who is, owns the animals and is making the manure, and the other is the project developer, because those are the two main kind of stakeholders we tend to work with when it comes to these discussions. Because the farmer, it's typically his or her farm. They've owned that land. Their families probably own that land for generations. They're invested in running a good operation and being responsible stewards of the environment. But they know that manure hauling and spreading is probably one of their biggest headaches, right? So by implementing a manure treatment system that captures ammonia, they can reduce their spreading and hauling costs. But really, a lot of it is around eliminating the management of their lagoon and the challenges that they experience with it. So by reducing volume, in this case, by making water that then leaves the system by going back to the cows to drink or going into a river, they get significant volume reduction, and that reduces the headache. It essentially takes a lagoon that maybe only provided 200 days of storage, and now it provides more like 350 to 400 days of storage. So it can dramatically help improve that side of the operation. I think when we concentrate nutrients and we take that pressure off farmers for managing their lagoon levels, I think we get better nutrient application and therefore less runoff. And so that can also lead to less trucks on the road, obviously, if we have lower volumes. But really about when you apply, I think, is a major component in the amount of runoff and the amount of uptake that your crops get. And you often apply manure, not because it's the right time of year or because it's the right time for your crops, but because your lagoon is full and you need to do something before it overflows and you have a much bigger problem on your hands. So if we've removed that volume pressure, you're then applying manure when it's the right time to do it. Obviously, if we reuse the water, we can conserve freshwater resources. That's a substantial benefit. And then, perhaps most importantly, at times is a new revenue stream. Farmers with milk prices and other stressors need to be creative and need to think of ways to sustain their business. And I think creating organic nitrogen fertilizers from ammonia that you were losing to the air anyways is a great way to do that. With sort of the other hat on, as a project developer, a lot of farmers today are being approached by project developers who are developing RNG projects to inject renewable natural gas, and that's great. But often they forget to think about the nutrients. So manure goes into the digester, developer makes gas, shares a little bit of gas revenue with the farmer, hopefully more and more as time goes on. And then digestate comes out and they say, here you go, farmer, back to you. And the farmer doesn't have any really improvement in that management. So I think something that developers can do is offer this kind of technology as a service to farmers and to their surrounding community to say, we're going to do this project to create renewable energy, which is great for the environment. But at the same time, we're going to use a piece of that revenue stream to invest in advanced nutrient treatment. And sometimes there's great incentives to do that. Sometimes there's not. And I think we want to encourage more incentives to do that. And maybe it's phosphorus trading, maybe it's water credits. There's lots of ways you could structure that. But sometimes it's just the right thing to do for those farms. And you have farmers who will say, I can either stay here and keep farming if we do something different, or I have to pick up and move somewhere else because I can't keep farming the same land the same way I've been doing for the last 50 years. So I think there really is a place for project developers who are investing sometimes lots and lots of capital in these farm projects to do something besides just business as usual. Even if that pro forma, return doesn't look quite as good as it could, I think there needs to be thought put into that nutrient management side. But I think one way to do that is to look at CI scores and other things that go into the valuation of a biogas project and how this technology can help. So for example, capturing those volatile solids with the ultrafilter can dramatically improve your CI score, or you can make additional gas. And we've proven that with digestion studies. So there's ways to provide the benefit to the farmer, let's say in nutrient management benefits and volume reduction benefits, while simultaneously claiming benefits for the project's bottom line too. So it isn't just a sort of a trade-off. I think there's win-win on both sides. And then obviously the fertilizer sales or nutrient trading credits could be part of that as well. So that sort of summarizes it from those two perspectives. Obviously, there's the perspective of sort of the regulatory environment and the watershed and the environment that we always like to think about. But these are the two main stakeholders executing projects today. So I want to leave a few minutes for questions, so I will stop there. And if anybody has questions, please fire away.
Thank you, Dr. Levine. We do have time for a couple of questions, and we did have a couple that came through the chat. So the first one, the person that dropped this in the chat said, thank you for the presentation. Did you measure the actual change in methane production in the digester after refeeding the concentrate back into the digester?
Yeah, great question. So when we take that UF concentrate, what we've done is we've collected digestate, we've ultrafiltered it, and then we've put the permeate and the concentrate into a biological methane potential test, which is basically a mini digester for 30 days, and we've measured that gas production. So that's data that we would be happy to share if someone was interested in reaching out to us. But there is certainly, at most commercial digesters today, you're leaving a lot of gas value on the table because no digester is 100% efficient. And so we think there is value in concentrating those volatile solids and then being able to digest them. And you can also think of it the other way. You can take raw manure that's dilute, concentrate that with the UF, and then haul it to a digester as well. And that's something that we're working on in a few places where you have farms that are as far as 20, 30 miles away from a centralized digester, and we can ultrafilter manure and then bring it to the centralized digester, cutting the hauling both ways because we've now concentrated the manure, as well as made the digester itself smaller while achieving the same retention time.
Thank you. The next question was, with multiple options for dairy farms to do, it seems as if most of these options are left with the dairy's 2,000 or more cows. What is your recommendation on number of milking cows for your options?
Yeah, that's always a great question. So I love working with small farmers. We just launched a new line of containerized filtration equipment. So it comes in an 8x10 or 8x20 shipping container, and it's designed for smaller farms where we just sort of have standardized designs and pricing. So that can go down to 50 cows. It really just depends on what they're looking to do. When it comes to fertilizer manufacturing, that really does have to be typically on the larger side, maybe 1,000 or 2,000 and up. But in terms of just the filtration, if you just are looking at ultrafiltration or ultrafiltration plus water recovery, that we can scale down very well.
Okay. The next question: how many installations are actually discharging clean water to waterways? There's a comment. I assume that this number is different than the amount of installations that are permitted to discharge.
Correct. So right now we have only done one farm installation with a permit, which is the Majestic Crossing Dairy. But there are at least one other project that we're involved with that will be public very soon, where they have a discharge permit as well. So it's certainly not many yet. It's definitely a new, it took, and I think the Wisconsin DNR has done a great job kind of streamlining that process now that a few folks have been through it for this particular kind of application. But certainly it's, we hope it grows.
Thank you. And one final question that I saw in the chat: OMRI standards have some limitations on ammonia or ammonium-based fertilizers. Have you successfully labeled products from your projects as OMRI certified?
Yes. Yep. So the 605 product is OMRI certified. That is through a partner of ours, but that is being sold today and is certified. And then we're in the process of registering other products as well as we continue to develop them.
Okay, and we'll just give a second to see if there's any other questions coming through the chat, but I think that that was the last one. We do want to thank you again, Dr. Levine, for your great presentation.